Hello, everyone. This is Tara at Omnitracs, welcoming you to today's webinar all about big data and predictive modeling, and the first webinar in our 2016 Transportation Trends webinar series. Before we get started, I'll go over a few quick housekeeping items. You have joined in a muted conference mode, so to communicate with us, please type in the chat box to your right. Following today's presentation, we will take live questions, so you can type those in chat as well. Also, we will be recording today's webinar and we'll be emailing it to you after the event. So I'd now like to introduce you to your host and presenter for today. Dean Croak is Vice President at Omnitracs Analytics, and he has a great deal of knowledge to share with you today. So Dean, let's go ahead and get started.
All right. Good afternoon, everybody. Welcome to our first of 4 webinars on 2016 Transportation Trends. Today we'd like to cover 4 topics. The first one is big data, and is it really new or is it old technology? The other is big data in the context of predictive modeling. Predictive modeling is part of the suite of business intelligence technologies that we use at Omnitracs Analytics. Thirdly, we'd like to talk a little bit about big data in the context of a case study using electronic hours of service data. And most importantly, what do you do with all of that data once you've got it in a format that you can use? The topic of big data has become a little bit of a buzzword in recent times. The reality is that we've been doing this for about 10 years now, and a number of other entities in the industry have been doing it for almost as long. There's a couple of things happening that make it unique, and one of them is that the volume of data is growing at an amazing rate, and it's been exponential since the digital age took hold in the early 2000s. The basic idea behind the phrase big data is that everything we do in our lives is or will soon leave a digital trace of data, which we and others can use and analyze. The advances in capturing and analyzing big data allow us to decode things like human DNA in seconds, find cures for cancer, predict human behavior, foil terrorist attacks, pinpoint marketing efforts, prevent disease, and so on. But basically, big data refers to our ability to collect and analyze the vast amounts of data we are now generating in the world. But it's really a combination of everything we've been doing with data and technology for the last 50 years. What is different now is our ability to harness the ever-expanding amounts of data, which is completely transforming our ability to understand the world and everything within it. You might ask, so what's new here? Haven't companies and organizations captured and analyzed data for a long time? The answer is yes, but there are 3 things that are changing at the moment and making this phenomenon of big data very real for most of us. Firstly, the rate at which we are generating new data is amazing. It's almost exponential at the moment given advances with technology. The second is our ability to analyze large and complex forms of data that has been transformed in recent years using technologies that have only just become available to us. For example, in 2005, when Omnitracs Analytics started building predictive models, it would have taken us 50 hours of computing time to process 20,000 drivers. Today, we do that in less than an hour, and that's 50 times faster than we did 10 years ago. Thirdly, our ability to generate insight from what we call unstructured data or data in motion. For a long time, we've all been very good at looking at data that's structured in rows and columns, but with about 80% of our data unstructured these days, we have a great opportunity to look further into data and generate more insight. Unstructured data includes things like latitude, longitude, the constant stream of engine data we pull from our trucks, things like in-cab video, inwards, outwards facing, lane tracking technology, weather, even still frame images, pictures, and in-cab messages between drivers and the back office from the telematics device right through to email and other documents, all unstructured data, all generating huge amounts of value. To give you an example, today we build text analytics models that can tell if a driver is more or less likely to quit based on just the words they use when they communicate with their dispatchers. And that's technology that wouldn't have been available in the last year. If we look at big data at Omnitracs in the context of today's webinar and commercial transportation, our customers produce around 29 gigabytes of truck data every day. Now, that's not a lot of data compared to companies like the Weather Channel, for example, but if we use a unit of measure to put 29 gigabytes of data in perspective, and if we laid that out end to end, that data would stretch 45,536 miles, or about twice around the Earth every day. Now, that big data set allows us to do much more than we could even a year ago. Today, we offer things like compliance and safety from just the 1 hours of service applications. And within the next year, we'll be able to provide things like ongoing driver risk scoring, custom safety messages to drivers in the cab in the form of virtual co-driver technology, plus route optimization, including alternate scheduling practices, avoidance of black spots where trucks have critical events, maybe there's accidents in snowstorms. These sorts of things will use very clever vehicle-to-vehicle technologies that are already embedded in some of our automobiles. And all of this will happen in real time in the next year. We aren't there yet in terms of real-time production of data, but in the next 12 months with the advancements in technology, we'll be providing predictions down at the hourly level based on real-time traffic flows, weather patterns, average road speed, how tired drivers are, amongst the number of data points that we'll be pulling from our various systems. So to give you a sense of how we do all of this, at Omnitracs Analytics, we receive vast amounts of electronic data from various systems across all of our customers to build our predictive models. And the data set includes things like driver demographic data such as hire date and driver type, company operational data such as trips and miles with which the driver is associated, driver pay data, driver log data, which all get added to a much larger data set, including data from our external data warehouse, including traffic, weather, census data, and any other publicly available data source that might provide additional insight during the modeling process. Typically, we import several years of this type of data into our secure data center in order to build the models. But most importantly, it's important to note that we do not use any data that would violate HIPAA or EEOC regulations such as social security number, age, race, medical conditions, and marital status. Even though everything we do is discoverable, no driver can be personally identified in our database. On the bottom end of the screen, you can see that we have some dashboards. It's a fairly simple display that provides alerts. It's a workflow tool, displays model results. It shows you who drivers are at risk and suggests some various remediation techniques, such as whether the driver may have a skill issue or needs maybe some personal financial coaching and things like that. So there's an input layer which includes lots of electronic data, and the output layer is a dashboard that sits on our database, and then there's some business rules engines that provide remediation. In general, predictive models using big data technologies are what we'd like to call good news, bad news technologies. The good news is we can predict almost anything these days with sufficient data. But the bad news is you need lots of historical events for the algorithms or intelligent robots, as we call them, to identify the risk signatures that point to events like accidents, terminations, workers' compensation claims, drivers falling asleep, right through to trucks breaking down, just to name a few of the models we build. So for a model predicting accidents, for example, you will need either many accidents over 1 year of historical data or multiple years of data if you don't have a high accident rate. Typically, we pull about 3 years of historical data into our data set and map it into a format that we then can use for modeling. At a very high level, let's take a quick look at how a business intelligence tool called a predictive model works. It's different to predictive analytics. Predictive models are very different in that they're based on a very large set of data and do a couple of things around risk segmentation and decile management in order to identify the target population. If you look at any group of drivers, to most of us, they all look the same. If you looked out of your office today and you had a group of drivers in the yard, it's very hard to pick which one's going to have an accident or which one's going to terminate their employment, because to most of us, risk appears to be uniformly distributed, and most of them have the same risk profile. Risk segmentation is a concept we refer to where we separate out the risk profile of any one driver from another. It's no different to your insurance company with the car you drive to work, where your insurer might identify your risk profile based on the width of your street, the type of car you drive, the distance you drive to work, the time of day you drive, your rate of brake application, and they use that to segment your risk from other drivers in the portfolio. That's risk segmentation. The other thing we do is just a simple math technique called decile management, and that refers to breaking our driver population into equal populations or deciles, or 10% focus groups, as we call them. So on the screen there, you can see a representation of 1,000 drivers broken into 10% groups. And on the far right would be our low-risk drivers, and on the far left would be our high-risk drivers, i.e. those with the highest probability of an event. Now, if risk was randomly distributed across the driver population at your company, then we'd have a flat line, i.e. 10% of accidents would occur in 10% of the drivers. But we know that's not the case, but most of you have pretty good predictive models running inside your heads right now, and you often have the ability to identify drivers with different risk profiles to a degree. And when we build models, sometimes you would look at it and think, well, these drivers on the far right, I know then they're pretty safe, but there's a few on the left here that maybe I need to look at a little bit more closely. The reality is that predictive models look to differentiate the risk across the driver population with a high degree of accuracy. And in conjunction with segmentation, we're able to get what we call lift from right to left, which isolates drivers with the most accidents in the highest risk 10% group. In the case represented here on the screen, drivers scoring between 91 and 100 on our model are 8 times more likely to have an accident than those scoring between 1 and 10, or least likely to have an accident. And that's how a typical predictive model is represented after we analyze thousands of data points and look at the historical patterns between accidents in a company. I'm using accidents as an example today because that leads into our case study using hours of service data. So let's look at a real-life example of risk distribution in a trucking fleet from one of our customers. In commercial transportation, there's a fairly standard risk distribution across any population of drivers, and it's not random where you'd expect to see the same rate in any group. If you take a look at the results on the screen, you can see that drivers our model scores least likely to have an accident have the lowest accident rate at 1.56. And the 10% of drivers that score the highest have an accident rate 13 times higher. And that's how you focus your resources and programs with the right drivers at the right time with the right intervention strategy. This way your message doesn't become white noise where you attempt to contact all drivers with the same message over time. Drivers tend to get desensitized to the same message. And what really works is just like a change-up in baseball. It's when you can actually send a tailored message to a driver and have an interaction that's very different month to month with different drivers. Put simply, a predictive model using big data is really just a list of drivers that point to those who have the highest probability of an event in any given time frame. But really that's just the start. What we can share with you after 10 years of building models in commercial transportation, we've determined that it's part art and part science. The science part, including math, data, technology, statistics, and algorithms, we've become very good at. But that's the least important part of the process because up until this point, the data is of little value unless it's used to make solid operational decisions to alter future events. The art part is where you, the client, comes in. And unless there's an effective method of communication between drivers and management, all of the big data, technologies, and terabytes of data in the world won't make any difference. There has to be a culture of communicating with drivers at the right time and engaging with them to affect outcomes. So it's really a cultural product that we've developed that's highly dependent on interactions between drivers. So that's predictive modeling 101, if you like. It's based on lots of data brought into a database. We look at the patterns of past events. The model could be based on things like miles, pay, DAT physicals, loads, prior jobs, hours of service stops. And then what we do is we score drivers on their probability to have accidents. And typically, the drivers that the model scores the highest have the highest accident rate. And that's the group that we focus with. Typically, most of our customers talk to between 10 and 25% of their drivers each calendar month. So that's modelling. Let's look at now a case study. And with that background, let's think about how we use data to build predictive models with a case study of very clean, consistent data across the majority of fleets. This has been a very elusive target for our company for a long time because most of the predictive models we build and the predictors are cultural. That means that for one truckload carrier to another, only about 15% of the data points in terms of predictors are common from carrier to carrier. About 80% to 85% of all predictors of things like accidents or terminations are related to the culture of the company. And for a long time, we've been unable to build a model that could be applied to all fleets so that we could get fleets less than, say, 500 drivers involved in the technology. So this case study will show how traditional compliance data from an electronic log could be used to generate additional insight. With the rapid uptake in electronic logs and evidence from drivers that being compliant doesn't automatically make them safe, we have an opportunity to use this vast set of emerging data using big data technologies to turn compliance data into safety data to provide an additional safety net from drivers. Being compliant, the challenge is that it doesn't make you automatically safe. In fact, drivers tell us it's the opposite, and depending on the time of day and of rest, sleep personality of the driver, sleep disorders such as sleep apnea, length of haul, radius of operation, and work-to-home time balance, we find that the hours of service regulations aren't really a one-size-fits-all solution, which is why we think that most fleets in commercial transportation need to look for those drivers that fall outside of the norm. And typically in our data, when we look at large numbers of drivers, we find that about 12 to 15% of any driver population will be what we considered outliers, or with levels of risk where there's things like a 6 to 7 times higher probability of a DOT recordable event. And all of that is identifiable from within the electronic log record. So let's dig a little bit deeper. What we've been able to build is an accident severity model using electronic logs. And with the ELD mandate imminent, there's certainly a growing need to offer new and inexperienced drivers much more than compliance if they're to be safe. In our database of customers, about 3 years ago, experienced drivers made up about 30% of the population. Today it's down to 5%. So what we're seeing in most of our fleets is there's a higher uptake of inexperienced and student drivers. And of course, if you take someone who's been sleeping mostly at night during their prior occupations, and then you put them into an over-the-road situation or a dedicated slip seat operation where they work 12-hour schedules, they're going to find it very difficult to adjust their sleep patterns. So why? Why have we done this? Well, the challenge is that, we find that drivers can be 100% compliant to hours of service regulations, but unintentionally sound asleep at the wheel simultaneously. So there's no direct correlation between the two. And it turns out that electronic logs provide a very rich source of predictive data that point directly at severe accidents, not just compliance. In fact, each driver's log page produces about 48 inches of data, to be precise. At our company, we've been able to identify that about 22% of the frequency or number of accidents account for about 88% of the cost of claims. And this is a number that we've been able to replicate across 4 different countries across the world. It's pretty much the same numbers pan out in terms of, severe accidents tend to be very low in number but very high in cost. So that's the severity model target, and that's sort of the background why we're doing it. How we developed the model, we used a 10-year study of nearly 208,000 accidents and found that close to 28,000 of those were what we class as severe. Now, in our world, we look at severe accidents as loss of control accidents, and they were about 13% of the total, and 87% were what we'd call distraction-type accidents. And the loss of control accidents are really where the driver is most likely not in control of the vehicle at the point of impact, making it a very random event. The difference between distraction and events and loss of control events, distraction events tend to be more behavioral, loss of control accidents tend to be more physiology. And what we find with distraction accidents, when you look at the risk signatures, the driver is usually trying to make some sort of avoidance maneuver at the point of impact to minimize damage, whereas a loss of control accident, the driver is actually disconnected from the driving task, making the outcome a fairly random event. In terms of building the model, we had just over 6,000 accidents where we had a driver log associated to it, and we used a massive set of data which contained 1.7 million months of driver logs. And to use that same unit of measure, if all of those logs were laid out end-to-end, this model's been built on data that would stretch 39,000 miles. So it's a very big data set that we wouldn't have been able to look at even 2 years ago. What the model's predicting is this. It's predicting accidents where we consider that there's no control of the vehicle, the driver is completely disconnected from the driving task, the driver takes zero evasive action prior to impact. Most importantly, the driver could have seen the point of impact 6 to 7 seconds prior. If awake and alert, they could have avoided it. And that's a good yardstick to use if you're trying to figure out whether your accidents were fatigue-related or not. And lastly, the driver makes no attempt to minimize damage at the point of impact. And most of these are physiologically related, not behavior, as I mentioned, and usually due to things like lack of sleep, disrupted sleep patterns, chronic fatigue, severe fatigue, things like circadian rhythms, time of day, even extends to sleep disorders like sleep apnea. And the accidents we're trying to predict using electronic log data are what we call our big six, which are things like rollovers, run-off road accidents, head-on collisions, jackknifes, side swipes, and rear ends. They all have a very distinct risk signature. You know, high-speed rear-end collisions, for example, happen typically when the driver's eyes are wide open, but their brain is asleep, which means that they can make complex steering maneuvers, but they can't process that as a vehicle going at a different rate of speed ahead or stopped. Things like rollovers, run-off roads, head-on collisions, jackknifes, side swipes, typically the driver is going to have a microsleep event where the brain goes to sleep for periods of 4 to 5 seconds. Studies have shown that the average microsleep in commercial trucking is about 5.4 seconds, which means that's about the time that the truck travels with the driver asleep before their head nods. Generally, the head nod happens after the neck muscles collapse and the brain and the head tilts forward. So for most drivers, they're unaware of this, that the head nod is actually the wake up, not the sleep. And typically that takes about 4 to 5 seconds before it happens. You see things like hit guardrail to the right or a 4-degree drift to the left, which could end up in the median. And some of you might code those as wreckers in your database. But essentially things like, you know, a run-off road where you hit a guardrail and a run-off road where you run into the median are both drivers that fell asleep. So what we're trying to do is predict the physiological event that preceded these events. And to give you a sense of how well the model predicted, we conducted a blind validation of 535 accidents and predicted quite a few of these big six severe accidents. You can see that we predicted some side swipes, rear ends, run-off roads. The data showed us that about 22% of these 535 accidents were in fact what we call severe. So this was a retrospective validation where we held this data out, we built a model, and then we said, okay, if we were in production predicting accidents in October, November, and December last year, what accidents would we have predicted? And you can see there that we predicted a lot of hit animal events. And of course, a lot of animals are nocturnal, they feed at night. But the reality is that a hit animal could have also been a hit person, it could have been a hit vehicle on the shoulder. So in our model, we consider a lot of these accident types to be where drivers that are tired have these sort of events that all have this risk signature. What we also found was that these 22% of the accidents made up 88% of the cost, but the average cost was staggering. It was about 9 times higher than the industry average. So it was good proof for us that the model was predicting very well. And if we look at the time of day that they occur to further validate the model, we found that 75% of the accidents that we predicted just using driver's logs occurred between 11 p.m. and 7 a.m. when most of us are sleeping. So it was good proof that the model was predicting accidents around the time of day when really bad things happening. You can see a couple of circadian impacts there. You can see the post-lunch circadian dip around 1 to 3 p.m. and then the other one between between midnight and 8 a.m.
Sorry.
I'm really mad at Excel. They screwed us on this part.
Excuse me, if you could please mute your lines, we appreciate it. Thank you.
Oh, okay.
Good thing you weren't saying anything bad about me. So to give you a visual representation of how the model works, what I'd like to do is take you through a process or a flow chart just to give you a feel for what we do with data that from a truck equipped with in-cab telematics and hours of service data. So very simply, we load the data into our warehouse. It's all electronic. We could take data from a scanned-in paper log that's scanned into software that turns it into an electronic record, or we could take data directly from an electronic log, even down to the daily or hourly basis. We load it into our model. We run it through a production process that takes seconds, literally seconds to score drivers. We run it through the model. We push it out to a dashboard. The driving center is our technology that's a dashboard that we'd embed on your side of the firewall so that you could look at it and then push messages back to the driver and provide sorts of interventions that might limit their probability of high-speed accidents, loss of control accidents. And you might do things like, there's no question that accident severity is strongly related to physiology, and based on our experience, one of the most important things you can do is provide drivers with better sleep opportunities. There's no substitute for naps and good periods of night sleep, good work-to-rest balances to reduce accident probability. Our program is underpinned by sleep science education, where we conduct workshops for drivers and managers so that they understand how to use all the technology. But all of that up until this point is great, but it leads us to the most important question. What do you do with all this information now that we're making these predictions? Because if I can tell you which drivers in your fleet are most likely to have a severe accident, the biggest question we face is, what do I do with that so that I don't adversely impact production? What we know is that well-rested drivers do more miles safely. That's without doubt. Our drivers that we put through our programs have far fewer accidents. They do about 10% more miles per tracked a week. They have fewer service failures. They're more on time. And they're about 30% less likely to quit. So there's some serious value from being able to interact with drivers. And one of the big messages is that this will actually improve productivity and retention in addition to improving safety. There's a couple of things we give you in terms of our dashboard. It's called the Driving Center, where you'd log into it. It would show all of the drivers in your fleet and their current score. This is something that everybody could have access to, or you could limit access depending on passwords and unique login IDs, depending on which drivers are attached to which managers. One of the most important things we provide is what to do with it. And this is the art part of the science and art equation, where you'll need to know what to talk to the driver about. And what the dashboard includes, just some general information about the driver, their score, subjects to cover. We've got some standard subjects in there that you could cover in terms of sleep basics, night shift, day shift strategies, tips for drivers for driving at night. And then most importantly, there's a section that I've covered up there because of some proprietary information. What are the reasons behind the score? So we'll break down 7 or 8 of the predictors and tell you what it was that caused the driver to have a high score. And that leads you to what do I do about it to change the driver's probability of a loss of control accident. The most important part is the action plan. When you create an action plan, you log in the date of the conversation, you type in some notes, and then put in a follow-up so that you can know that you were successful over time. We have text analytics scorecards that will measure the sentiment of the calls and the conversation based on the words that get typed into the dashboard. And the end users, whether it's a fleet manager or a safety manager, would just simply log in a follow-up date to catch up with the driver next week, or when they're back home, or when they're back in that evening, and then click complete. And that action plan has been put in place for that driver. So that's how the dashboard part of it works. And that brings us to the conclusion of today's webinar. We've covered in pretty short time some things like the subject of big data. We learned that it's really not new. It's both new and old technology. We use predictive modeling as an example of big data technology. We looked at what we call data in motion as opposed to data at rest, using hours of service data. And finally, we covered some techniques on how to make the most out of your data. And before we take questions and hand back to Tara, I'd just like to remind you of the registration process for our upcoming series of webinars. Our 4-part series of transportation trends continues through to December, and you've got the links there to log in. So I'll hand back to you now, Tara, for more questions.
All right, thank you so much, Dean. Great presentation. We'll now move on to questions. So for everyone on the line, please type your questions in the chat box to your right. I do realize we're a little over on time, so we'll run through a few quickly and then follow up with everyone else offline. So the first question is, how do you get all of this data into your system?
Good question. We have software engineers that would visit a client's premises and map all that data to our standard data extracts. So we do all the data mapping from whether it's an Excel spreadsheet or a Windows PC system right through to complex AS400s or various vendor software applications, mainframe operating systems.
Thank you. And how current is the data that you use in the models?
The data is real-time, so we get electronic data feeds from our customers typically around 3 a.m. every morning. So it's certainly based on the last 7 to 10 days of work. But we get a daily feed. Some of our clients feed us through the data every hour. So it really depends on the operational requirement and how often the fleet would like to interact with drivers.
Great, thank you. And this question is, how long have you been doing analytics? So just a real brief history, if you don't mind.
Yeah, we were a startup company in 2005, so we started predicting accidents for insurance companies and then quickly morphed into working with trucking fleets. We actually started building fatigue models in 2001, so we're coming up on 15 years in the predictive modeling space.
Great, thank you. And how much data do you need to build a predictive model?
It's a great question. So typically we like to say 3 years. For fleets that don't have a lot of accidents, you'll need more years. You may need 5 years of electronic data. But for some of our very large fleets, we've only needed 1 year of electronic data across all of their systems. So it really depends on how many historical accidents or terminations or workers' comp claims you've had in the past. But work on 3 years as a guide.
Okay, thank you. And this question is, what about driver privacy?
That's a good question. So given that we don't touch anything like Social Security, name, sex, marital status, race, anything like that, no driver can be identified in our database. In fact, most of our clients even encrypt the driver ID on the way out of their shop. So you couldn't really identify anybody from our data.
Thank you. And how often do the models run?
So typically at the moment we run the models either weekly for smaller fleets, and for our large customers we'd run them daily. And within the next year we'll go to hourly. So at the moment mostly weekly, you could say weekly, hourly, in the future weekly now, and some of our clients run them every month, but weekly would be about the best average, I think.
All right, thank you. Now we have time for one more question, and let's see. Is this data discoverable in the event of litigation?
Absolutely, yep. So anything we do is discoverable. We've had lots of precedents where our clients have had to hand over this information to plaintiff attorneys. The good news is that this is a very defensible safety technology, because what you're doing is but you can demonstrate in a court of law that you're not only meeting your legal requirements, but you're acting over and above what's required, and that you can show them through your documentation of this system that you've done everything you could to have prevented the accident through these additional technologies that you put in place.
Great. Thank you so much, Dean. So we're going to have to wrap things up now, so thank you everyone for joining us today. If we did not get to your question, we'll follow up with you offline. And as Dean mentioned, we do have more webinars coming up in the series, including more about the accident severity model with Dean on December 16th. So thank you, and until next time.